Hello, this is Alan Burton. I was the principal investigator for a CERDIP project, ER18C41181. The title was Proof of Concept for the In Situ Toxicity Identification Evaluation Technology for Assessing Contaminated Sediments, Remediation Success, Recontamination, and Source Identification. This was a CERDIP Exploratory Development Project, sometimes called a SEED project. The SEED project addressed critical DoD issues regarding the need for monitoring tools that are effective at providing certainty in the decision-making process in regards to several risk determinants such as causality, bioavailability, source ID, and fate across ecosystem compartments. The In Situ TIE can address all of these. It's a biological fractionation protocol that systematically identifies chemical classes that cause toxicity in either overlying water, pore water, or outfall effluents. The system separates chemical classes of contaminants of concern that are frequently linked to adverse biological effects, such as organics, metals, ammonia. The objective of the project was to demonstrate a proof of concept of this accurate field methodology that links chemical class exposures directly to effects, allowing for more cost-effective monitoring and remediation decisions. This prototype 3 is a robust deployable system that allows for consistent and sensitive measures in pumping rates of the ambient waters that pump through a diagnostic array of resin treatments. The design is actually shown in the audio figure and includes a bottom chamber that contains the different chemically selective resins. Water is gently pulled through the resin with the pump and passes into an overlying chamber that contains test organisms. We've successfully tested several marine and freshwater invertebrates and also developed a larger chamber for fish embryo and larval testing. The water passes through this exposure chamber and then is collected in the sample bottle. The pumping is slow and only for 24 to 48 hours because we don't want these resins to become saturated and allow chemical breakthrough. The system includes a case with 4 peristaltic pumps, battery, and pumping control rate panel. These collect through tubing to the array of iTIE chambers, usually isolating 3 to 4 different types of chemicals. The current battery of resin separates ammonia, heavy metals, and organics such as PFAS, PCBs, and PAHs. After the chambers are retrieved from the field, we measure the endpoints of the organisms to assess if there's any toxicity, and then one may take the water samples and the resins and chemically analyze those to see which chemicals the organisms had removed from their exposure. We established a proof of concept. It appears to be a more sensitive and accurate system at detecting toxicity than the traditional lab-based US EPA TIE. It's a novel assessment tool and we believe should be a standard diagnostic technology at chemically contaminated sites. An evaluation was made of resources required for doing this test versus the traditional lab TIE, and we found it took 47% less time to do the in situ approach. The lab TIE also has a high potential for false negatives relating to lab manipulation, sampling related artifacts that can change chemical bioavailability, speciation, and toxicity. This would result in data that are misleading and may result in poor decision making for the site manager. From a strategic assessment approach, the iTIE should only be used in a tier 2 or 3 level after toxicity is identified in a tier 1 assessment. Most sites contain a plethora of chemicals which may be contributing to toxicity. So the iTIE helps the site manager focus on which chemicals are of greatest ecological concern. It can also assist with source ID of toxic chemicals, whether they're coming from sediments, caps, ambient waters, storm waters, or outfalls. Before the iTIS can become a standard diagnostic technology, we should do some additional research to refine the pore water sampling option, to improve the deployment logistics for getting this system into the pore water. We want to use a diverless system to reduce costs. We'll continue to optimize resin selectivity for various types of chemicals and look at the depth limitation. Probably up to 20 meters will be its capacity. And finally, we would like to expand the sublethal chronic toxicity endpoints for invertebrates and fish. For more information, please see the report and related journal publications that come from our lab. Thank you.